Hello friends, today we are going to see the basic concept of optical amplifier, that is the important point of chapter number 5. So the basic concept of amplifier, it is used to increase the strength of any signal. That is the basic function of amplifier. So in case of electrical signal, we have used the amplifiers to increase the strength of the current. Whatever is input current given, its strength it is increased and we get the amplified signal at the output. Similarly, in case of optical amplifiers, it will increase the strength of the optical signal that is given as input to the optical amplifier. It is by default, it will increase the strength of optical signal whatever is given as input to the optical amplifier. So the next question is why we use the optical amplifiers. So whenever we are transmitting the signal for short distance transmission, the amplifiers are not required. But whenever the question comes to the transmission of signal for long distance transmission, there are losses in the optical fiber communication system. That all the losses we have studied in chapter number 2 in detail. So in compensate with or in order with compensation with the attenuation losses, we have to use the optical amplifiers. So usually when the transmission distance it is greater than 100 kilometers, we have to use the optical amplifiers. Initially, the system which was used to amplify the optical signal, that is illustrated in the diagram. So optical signal is given as input to the optical fiber. Then the next block is optical to electrical conversion. So in this process, the basic point was directly the optical signal is not able to get amplified. First, whatever is the input optical signal, you have to convert it from optical into electrical signal form. Then the electrical signal is amplified with the help of electrical amplification process. Then the amplified electrical signal is again given to the optical to electrical conversion, and then it is we get at the output the optical amplified signal. So the basic process it is like that. Optical signal in, that is given to optical to electrical conversion, it is converted in the form of electrical signal. Again that electrical signal is given to the transistor or any electrical amplification device. Then amplified electrical signal is given to the electrical to optical conversion, and then the amplified optical signal we are getting at the output. So several types of amplifiers previously used which were having the conversion process from optical to electrical and again from electrical to optical. That is the previous method used. But when the new concept of optical amplifier was invented, the conversion part that was removed. So that is the basic difference between the traditional method for amplification of light and the current methods for amplification of light. So in the optical amplifier, whatever we are going to see, this conversion process it is avoided. So directly we are able to see the conversion of optical signal into amplified optical signal without its conversion into the electrical signal. So basically here in this session we are going to see two types of optical amplifiers: semiconductor optical amplifiers and erbium doped fiber amplifiers. That two amplifiers are there in our syllabus: semiconductor optical amplifier and erbium doped fiber amplifier, that is usually known as EDFA amplifier. But before starting with the two types of amplifier, let us first see what is the basic working principle of optical amplifier. So in the diagram, the basic working principle of optical amplifier it is shown. So there are mainly 3 points in the diagram. First one, it is input optical signal given to the optical fiber. So whatever is the weak signal which we have to amplify, that is given as input to the input optical fiber. So through the optical fiber, it is given to the optical amplifying medium, and the output of optical amplifying medium, it is the boosted optical signal where the strength of the optical signal it is increased, and through the optical fiber at output we are getting the optical amplified signal. So the new point in this diagram, it is optical amplifying medium. So that is the basic point in the optical amplifier where the main amplification process take place. So all of us, we have seen the laser basic working principle. In that there are 3 points: absorption and radiation of light, population inversion, where for population inversion pumping process it is used, and third one it is the optical feedback and laser oscillation. That same pumping process it is used here, through which the amplification of light it is taking place. So the basic concept of pumping it is, so already we have seen in the population inversion concept and basic working principle of pumping process. So pumping process means we know that most of the light we get at the output, when transition of electron it is there from higher energy state to lower energy state, means we want our expected condition is n2 should be greater than n1, but the actual condition it is n2 it is less than n1. So we are inverting that population of number of electrons, that's why it is called as the population inversion, for more emission of light. And to achieve that population inversion we are using the pumping process. Pumping process means initially we are forcefully making the more number of electrons to get accumulated in the highest energy state, and then we are making the transition of electrons from higher energy state to lower energy state as per our requirement. That is the pumping process. So same process it is used in this optical amplifying medium, and through that process or with the basic working principle of laser, where the laser stands for light amplification by stimulated emission of radiation. So with the basic working principle of laser, the light it is amplified in the optical amplifying medium, and we get the amplified optical signal at the output, and through the optical fiber we are getting the amplified signal. This is the basic working principle of optical amplifier. Now there are 3 types of amplifiers are mainly used, as we discussed: semiconductor optical amplifier, fiber Raman and Brillouin amplifiers, and rare earth doped fiber amplifiers. That means it is EDFA, erbium doped fiber amplifiers. So all the amplifiers they are having the basic working principle same, whatever it is explained in the diagram. Only the change is there in their basic materials, whatever we are going to manufacture the optical amplifiers. So first we will see the semiconductor optical amplifier. So whatever is the basic diagram illustrated, that is same for semiconductor optical amplifiers. We will see what are the characteristics of semiconductor optical amplifier. So it is polarization dependent, require polarization maintaining fiber, relatively high gain. So here the gain stands for the ratio of output optical power to the input optical power. So if that gain it is more, the efficiency of optical amplifier it is good. So high gain it is maintained approximately around 20 dB. Output saturation power it is 5 to 10 dB. Large bandwidth it is provided by this amplifier. It can operate at the operating wavelengths are separate for specific types of amplifiers. It can operate at 800 nanometer, 1300 nanometers and 1500 nanometers wavelength respectively. Then it is compact and it can be easily integrated with other devices. It can be integrated into arrays. High noise figure, but the last disadvantage it is having the high noise figure and crosstalk levels due to non-linear phenomenon such as wave mixing. So the main disadvantage of this it is having the high noise figure. Noise figure is ratio of Sn of input to Sn of the output. So high noise figure we are getting in this, and crosstalk levels are also more. So this last feature restrict the use of semiconductor optical amplifier. So in the diagram, the structure of semiconductor optical amplifier it is given. So input signal whatever is applied, that is the weak signal, and amplified optical signal we are getting at the output, and whatever is the amplifying medium, that is shown as nothing but the semiconductor cavity. It is shown at the center. So it is having the similar structure to the laser cavity. Whatever is the semiconductor cavity, it is having the similar structure to the laser cavity. It is used as a discrete amplifier. They can be integrated into arrays of amplifying, switching and grating devices. Finding applications in all optical 3R regeneration system. So that is most commonly used optical amplifier in the applications. And as we have seen, the main drawback, it is high noise figure. Another drawback, it is having the limited in operation below 10 gigabits per second. So high rates are possible with lower gain. So these two are the disadvantages of the semiconductor optical amplifier. So instead of semiconductor optical amplifier, the most commonly used amplifiers in the practical, it is rare earth doped fiber amplifiers. That is one of the common example in that, it is erbium doped fiber amplifier. So rare earth doped fiber amplifiers are finding increasing importance in optical communication systems. Perhaps the most important version is erbium doped fiber amplifier. So as we discussed, EDFA, it is the commonly used under this category of rare earth doped fiber amplifiers. Due to their availability to amplify signals at the low loss 1.55 micrometer wavelength range. So as we have seen, the wavelength range where we are getting the minimum losses, that is 0.8 micrometer to 1.55 micrometer. So in the range where we are getting the less losses, that light can be amplified by using the EDFA amplifier. So as we have seen the characteristics of SOA amplifier, similarly we will see the characteristics for EDFA amplifier. It is advantages, first we will discuss. So advantages are high power transfer efficiency from pump to signal power. So efficiency, obviously it is ratio of PO divided by PIN, output optical power divided by input optical power. It is greater than 50%. Wide spectral band amplification with relatively flat gain, that is greater than 20 dB, useful for WDM applications. So in next chapter we are going to see the concept of wavelength division multiplexing. As we are using time division multiplexing and frequency division multiplexing for electrical signals, for optical communication we are using the wavelength division multiplexing. For that application, this EDFA, it is useful. Then saturation output, it is greater than 1 milliwatt. Gain time constant, it is long, more than 100 millisecond to overcome the patterning effects and intermodulation distortions. So whatever is the initial delay to convert, or initial delay for amplification, that is less, and we are getting the less distortions or less noise in this EDFA amplifier. It is having large dynamic range, low noise power, polarization independent. As the SOA, it is polarization dependent, this EDFA, it is polarization independent, and it is suitable for long distance application. These are the advantages. So in exam, the comparison, it is asked between the SOA and EDFA. So whatever are the advantages and disadvantages, that points are helpful for that. Then next, it is disadvantages of EDFA. It is relatively large devices, kilometer lengths of fiber, not easily integrated with other devices. So its compatibility to get connected with other devices, that is less. Then amplified spontaneous emission. There is always some output even with no signal at the input due to some excitation of ions in the fiber. So ideally whenever there is no any input signal, the output signal should be 0. That is not practically happening. Though the input power is 0, some amount of power we are getting at output. That is called as the spontaneous noise, that is present in the EDF amplifier, which is not present in SOA amplifier. Crosstalk effects are also there. Gain saturation effects are there. So these are the disadvantages of EDFA amplifier. So the basic working principle or basic structural diagram for EDFA and SOA, it will be same. Only here we are going to see the energy level diagram for erbium doped silica as shown in the diagram. So the different energy levels. So as we seen, the transition of electron, or whether we are getting output as emission of light or absorption of light, that depends upon the transition of electron from higher energy level to lower energy level, or lower energy level to higher energy level. So here whatever is the energy level diagram that is shown, that is almost similar to the pumping process that we have seen in case of the laser. So here 3 levels are shown. We can say the first one, it is having the lowest one, it is having lower energy state. second one it is having the higher energy state, and third one it is having the highest energy state. So whenever the initially it is shown that the arrow it is shown from bottom to the top, so that indicates the maximum number of electrons are forcefully excited in the higher energy level, that is called as the pumping process. And then from that highest energy level we can make transition of electrons to the lower energy level as per our requirement. So pumping is primarily done optically with the primary pump wavelength at 1.48 micrometer and 0.98 micrometer. So that are the wavelengths specified in that particular process. As indicated, atoms pumped to the 4I level band decays to the primary emission transition band. Pumping with 1.48 micrometer light is directly to the upper transition levels of the emission band. Semiconductor lasers have been developed for both pump wavelengths. So here whatever is the diagram that we can summarize as similar process as that of the pumping concept. So lowest level it is the lower energy level. From that we are exciting more number of electrons at the highest energy level, and as per our requirement we are making the transition to the lower energy level. Then pumping can be also performed at 820 and 670 nanometer with aluminum arsenide laser diodes. Pump efficiencies are lower, but these lasers can be made with high output power. So these are the basic two types of the amplifiers: semiconductor optical amplifier and erbium doped optical amplifier. So next we will see some of the characteristics of optical amplifier or performance parameters of optical amplifier. First one, it is typical absorption or gain spectrum of erbium doped fiber. So here the graph it is mainly about loss or gain, and that is versus the wavelength. So how the gain changes with respect to variation in the wavelength. So on x-axis we are having wavelength, and on y-axis we are having the loss or gain mechanism. So as the wavelength is increased, the absorption, that is losses, also increase, and gain also increases up to a particular wavelength. So in that diagram if we see, as the wavelength changes from 1.51 micrometer to 1.53 micrometer, the gain it is increased as well as the absorption it is also increased. But once it is crossing that 1.53 micrometer wavelength, it is exponentially decreasing. That is the relation between the absorption or gain versus the wavelength of the light. Since gain spectrum of erbium resembles a 3-level atom, it is possible to model the gain properties using this approach. So based on the wavelength range, there are 3 bands for the operation of EDFA that we are not supposed to go in detail with that. Just for your understanding, you can refer that this operation it can be divided into 3 parts. S band having the wavelength range as 1480 to 1520 nanometer, C band as 1521 to 1560 nanometer, L band 1561 to 6120 nanometer. So basically in this diagram, the relation between the loss gain versus wavelength it is shown up to a particular wavelength. As the wavelength is increasing, loss and absorption also increases, and after that particular wavelength, with increase in the wavelength, the absorption or gain it is decreased. In that way the graph can be summarized. Then in the diagram it is shown what is the general EDFA amplifier configuration. So how it is configured in the practical application. So firstly, the weak input signal is given through the coupler to the EDFA amplifier. So all of us know that device, coupler. We have seen that in the optical joints. So coupler is a device which is used either to combine the signals or to split the signals. So for the EDFA amplifier, the input is given through the coupler. One input to the coupler it is weak input signal, and another input it is laser. So laser it is doing the basic function of the amplification of the light. So that two signals are combined through the coupler and given to the EDFA amplifier, and at the output of amplifier we are getting the amplified light. That is the EDFA amplifier configuration for the practical amplifiers. So basic amplifier characteristics are again given, which already we have seen, but few of that are new that we will see. Rare or doped optical amplifier work much like a laser. So its basic working principle it is same as a laser. The primary difference is that they do not have the resonator. Amplification occurs primarily through the stimulated emission process. So that is the basic characteristics of the EDFA amplifier. Next, the gain coefficient. The equation it is there for the gain coefficient. So these are some additional points that actually those are not there in the syllabus, just but for more reference you can read whatever are the next points given, that are the additional one, but few of that we have to consider. The next parameter it is their amplification factor. So how we define the amplification factor of the optical amplifier? So it is defined as, or it is given by the term as gain, and it is the ratio of P out divided by P in. So P out is the amplifier output power and P in it is the input power given to the amplifier. So what if the ratio is higher, we can say the amplification factor it is more, or gain of the optical amplifier it is more. So that is important parameter of optical amplifier. Now this gain depends on various parameter. What is the length of the optical amplification media, which type of material it is used for manufacturing of optical amplifier. All these parameters are defining the amplification factor. So these are few of the equations related to that. Then the next performance parameter it is amplifier noise. So amplifier noise it is defined as, it is the ratio of signal to noise ratio of input signal to noise ratio of the output signal. So whatever is the input P in to input noise divided by P out to output noise ratio. So that is giving the final value of the amplifier noise, or same equation as that we are seeing for the optical, that we have seen for noise figure. So if the amplifier noise it is more, the performance of the optical amplifier will be degraded. So these are the two things or performance parameters, important performance parameters for optical amplifier: amplifier noise and the amplifier gain. So whatever are the next points, those are the other characteristics or the additional information given related to the amplifiers. So that you can just refer that for your understanding. Those points are not there in the syllabus. Related to our syllabus, up till we have to see only 2-3 points: amplifier basic working principle, why the amplifier is required, how it works, that is basic working principle. Then the structure, advantages and disadvantages of semiconductor optical amplifiers, and then structure, advantages, disadvantages of EDF amplifier, their comparison. Then the third type of amplifier it is not there in the syllabus, but just that is given in this PDF file, that is Raman amplifier, that you can refer for your reference. And two performance parameters of amplifiers we have to consider, that is amplifier gain, P, that is ratio of P out by P in, and amplifier noise. Okay, thank you.